All right, so we have worked volume problems. That's a triple integral of some function f of x, y, z over the region Q, and if it's a volume problem, we're finding the volume is dv, and that dv for us in rectangular, we have 6 choices, but for a majority of all of our problems that we've been working, we've been setting it up dz, dy, dx. If you do watch some of the videos from YouTube, all you have to do is type in triple integrals in spherical and or in cylindrical and spherical. If it's a foreign professor, he may always say Z instead of Z. So I guess it doesn't bother me too much, but I'm not going to change the way I do things. So, but Z is the same as Z. And you may hear them say maths, as in M-A-T-H-S. And whenever you argue with them, they'll say, well, it's mathematics, isn't it? So maths would be, multiple types of math. Anyway, that has nothing to do with this problem. So what we have to do, though, is we have to change this whole thing right here. We want to change that over to polar. And so when we change that over to polar, not polar, but cylindrical, we're going to have f of r cosine theta, r sine theta, z. That would be like x, y, z. And our differential changes to, just like it does with polar, r, with polar it's r dr d theta. Well, since z equals z, it's r dz dr d theta. And that r is like an r to the first power. So since there are 3 of those differentials, right, there are 6 different orders that we could put this in. But most of the time, we'll just leave it in that order. So what does that mean? That means that this innermost integral is going to have to be bounds of z. And z is going to be bound in terms of our old x and y. Remember, that's what we did for our triple integrals. If you have a dz here, you have to bound it in terms of x and y. Well, now we don't have x and y. So it's going to have to be bound in terms of r cosine theta and r sine theta. Okay? So that's the types of boundaries you're going to have here. Your book, to represent that, says h sub 1 of r cosine theta, r sine theta, to h sub 2, that's in the form r cosine theta, r sine theta. Now, once you integrate with respect to z, then it's basically going to just be a polar problem. All right, so when we integrate with respect to r, then of course, r is the distance. Now, that r still may be a function of theta, though, because theta is our last differential. So the r may be a function of theta. So your book writes from g sub 1 of theta to g sub 2 of theta. So it very well could be that those are numbers, that those are just, from 0 to 2 or something like that. Just depends on the problem. And then, just like other double integrals we've done and triple integrals we've done, the last integral that we do, we're going to be plugging in real numbers. And those real numbers, since this is theta, it's going to be radians, right? So it will be from some angle measure that is a radian to another angle measure that is a radian. All right, so let's look at this example of finding volume in cylindrical coordinates. Another good reason for maybe watching a video would be if you could find a video where somebody works out the rectangular equation and gets the answer, works out the cylindrical and gets the answer, works out the spherical for the same problem, gets the answer. We don't have enough time to do that. So, and of course I wouldn't make you work out all three of a very long problem on the test. But I don't think that it would be I don't think that a problem like this would be too hard for you to work on the test. Because once you have it set up correctly, the integrals aren't too bad. Just like any physics problem, right? Once you have it set up correctly, it's not too bad. The actual math. All right, so here's the figure that goes along with that. Find the volume of the solid region Q cut from the sphere by the cylinder. Now the reason why this doesn't look like a cylinder is because the cylinder would, if it was drawn as the entire cylinder, the cylinder appears that it would go outside of the sphere. Okay, so I mean it's cut off on this picture. You see how it's going down like that? That's because that's where it starts to touch the sphere. But this cylinder would actually go outside of that sphere. But what we're figuring out is the volume here that's inside the sphere. So that's kind of neat. We're not finding the volume just inside a cylinder. We're not finding the volume just inside of a sphere. If we wanted that, we could use high school geometry. We're finding the volume inside the cylinder that's also inside the sphere. All right. So we are going to set up a triple integral, and we are going to have to put boundaries on our z, on our r, and on our theta. So I have the triple integral. Now I don't have your function right here. You don't put a function right there. Times you would put a function right there would be like if it was the density of an object and we were trying to figure something else out. So there's no f that goes right here. F of r cosine theta, r sine theta, z. There's nothing there. But we will have what? R dz dr d theta. Now let's take our z and let's figure out the boundaries for our z. So look at this sphere right here. Now the z is going to be bound in terms of the r and the theta.
So is it from the square root of 4 minus r squared to negative square root of 4 minus r squared?
Yeah, with your second answer being the one on the left, the smaller one, right? So what we have to do is take x squared plus y squared, let that be r squared. And then if I move the r squared over, I'll have z squared equals 4 minus r squared, right? And if I take the square root of both sides, then I'll have plus or minus the square root of 4 minus r squared. So that's how my z is going to be bound. My z is going to be greater than or equal to the negative square root of 4 minus r squared, and it's going to be less than or equal to the positive square root of 4 minus r squared. So my boundaries are going to be from negative square root of 4 minus r squared to positive square root of 4 minus r squared. Okay? Now, do I know anything about my radius? We have the radius of the cylinder. Okay? So that is going to be, you know, if you think about the r theta plane, that would be like the xy plane, then this cylinder would be circular, would it not? Wouldn't it? So if we were looking down at this is of course the xy plane or the r theta plane. If we were looking down on that, it would be circular. So it would kind of look like this from the top. If you were looking down, that would be symmetrical. You know, imagine you were a little bird up here and you were staring down. Again, this is the xy plane, but we're also considering it to be the r theta plane. So if I'm bounding my r, all right, it's not going to have a z in there. My r is going to be bound in terms of whatever variable is left, theta. Well, we have r equals 2 sine theta. What does that look like? If you graph r equals 2 sine theta in cylindrical or in polar, is it not just a circle? I don't know. I mean, I do know. But let's look at it. Why not? I mean, we can already be done with this integral. I'm just trying to take it slow. All right, so remember this? 2 sine theta. See it? Now, this is not oriented in the exact same position because it is inside the sphere. So if we were looking down at this, I'm trying to think. Actually, I'm just trying to look at how the orientation is. So I got my positive x over here. So if I looked at it over here, you know, try to imagine, let's go back here. Where would it be? If this is the positive x and this is the positive y, translate this positive x, there's the positive y. So I guess that it would be like circular like that. I mean, I know it's skewed and it's not real circular, but it's kind of because we're looking at it in 3 dimensions. But it would basically look like that, right? If I was looking at it in 3 dimensions, looking at it kind of at the side. All right. So what is the boundaries for the r then? From 0 to 2 sine theta. Okay. Now what about the theta? The easiest thing to do, since the theta is the angle measure, like from this angle to this angle, the easiest thing to do here would be to use symmetry, and you know, if I did set that equal to 0, because that does intersect there at 0, you would get 0 and pi, but we're going to use symmetry, and we're just going to integrate from 0 to pi over 2, and then say our answer times 2. Now you may be able to get the answer another way, but taking half of that here, since this figure is symmetrical, taking half of the area really, and saying it times 2 would give you the same answer. And we're very familiar with values for 0 and pi over 2. Now, perhaps it would work if you went from negative pi over 2 to pi over 2. But again, just for convenience, I'm going from 0 to pi over 2. Yes?
The way you have it written out, that 0 should be at the bottom of the axis. You have your 0 right now,
Yeah.
positive y.
Yeah, this, you talking about right here?
Yes, sir.
Okay, well I was just translating this over. So yeah. Like this right here is the positive x, so that would be this. So this would be 0, this would be pi over 2, and this would be pi. Is that right? Oh, no.
That's right.
Is it? Okay, alright.
Like the little figure, the circles on the bottom.
Yeah, it is. It's on the x-axis, so it does need to be right here. If it would have been cosine, it would have been on the x. But it's sine, so it's on the y. Thank you. So, yeah, again, I guess I said negative pi over 2 to pi over 2, but I guess you might be able to do it from 0 to pi. It's just sometimes if you don't use symmetry, you'll get 0 for an answer if you don't set it up right. So you might want to try 0 to pi and see if you get the answer, just for fun, and see if that's the same answer as from 0 to pi over 2 times 2. Anyway, now it's just the calculus, the integrals. And the integrals are easy. So what is the integral for z? It's just going to be z, right? There's no z term there. So you just plug in the top boundary and the bottom boundary.
Whenever you times r.
Oh yeah, you'll have that r out there. It's zr, that's the integral, right? And evaluate that from negative square root of 4 minus r squared to positive square root of 4 minus r squared. So that's going to be r times what? What's the square root of 4 minus r squared minus the negative square root of 4 minus r squared? What is that? Are those like terms? Come on, math people. That's 2 of those times r. So that's 2r square root of 4 minus r squared. I didn't do magic. I just put the 2 terms together. Even though there's a variable in there, they're still like terms. Now, what kind of integral is that? u du, right? U equals 4 minus r squared, du equals what? Negative 2r. There's a r there, there's a 2 there, if you want to think about it like that. If not, bring out your 2, then bring out a 1/2, and they cancel out anyway. So you're actually only integrating the square root of u. Is that right? Of course it is. And the integral of the square root of u is equal to 2/3 u to the 3/2. Now you do have the what from the du you have to bring out. The negative. So that is going to be negative 2/3 u to the 3/2. And what was u? U is what I say u is. No, u is 4 minus r squared. I had somebody on my last cal test leave the u in and then evaluate it at the boundaries. That's the classic Eddie Britt mistake. You can't do that. Can't go full Eddie Britt. Never go full Eddie Britt. All right. So what am I evaluating that into, though? What did I just integrate with respect to? R. So I have to plug those into R. Here's another mistake that one of my students made, which you're not going to make. Don't ever just assume plugging in the denominator is going to give you a 0. Or not the denominator. The second boundary is going to give you a 0. Right? This plugging it in is not always going to give you a 0. All right. Because you end up getting what? 8. Right? So if I plug in a 2 sine, this is where your book just kind of skips a couple steps and goes, it's magic, you know. You end up getting, if you square that, you have, it's going to be 4 minus 4 sine squared theta minus, when you plug in the 0, you end up with the square root of 4 cubed, which is 8. Each one of those, and this one right here is what? To the what power? So you plug that in, and then it's to the 3/2. Oh man. So that's 4 times 1 minus sine squared to the 3/2. Well, what is 1 minus sine squared? Cosine squared to the 3/2. The square root of 4 cosine squared is 2 cosine squared theta. 2 cosine, not squared, 2 cosine theta, right? That's the square root of that, 2 cosine theta. And that's then raised to the 3rd power. Wow. So that's the integral. I have a 2 out here that disappeared. When I bring out that negative 2/3, it becomes negative 4/3. And then that's going to be 8 cosine cubed. So I have a negative 8 and I have a positive 8 cosine cubed. So that's 8 cosine cubed theta. Cosine cubed theta. What? Minus 8. So how do I integrate that? The integral of cosine cubed is sine cubed, right? No. The integral of cosine cubed is not sine cubed. I mean, I really don't want to have to work it out for you. I'd like for some good input here.
We do 8 times cosine cubed theta minus 1. See if we can figure out anything substitute.
Okay, like that.
That's the difference of 2 cubes.
That is the difference of two cubes, isn't it? It's kind of interesting that that's the difference of two cubes.
But I'm supposed to bring out a cosine, change some of the way the sine.
So if I bring out a cosine, well, how am I going to bring out a cosine? You would have 8 times. If you how am I going to bring out a cosine?
Would be
How about
Yeah.
for cosine what? Squared. We can't really integrate, but I mean we can integrate, but we can't really integrate this written like this. I'm going to bring that 8 out. When I bring that 8 out, that's going to be what? Y'all can at least do that, right? Come on. Feed me your knowledge. How about we treat that like two different integrals? And for this right here, that's cubed. That could be cosine theta times cosine squared. That's what Elijah was talking about. And then cosine squared is what? 1 minus sine squared. So you'd have 1 minus sine squared times cosine, because 1 minus sine squared is cosine squared, right? And then you have minus 1 over there. So now 1 minus sine squared you can distribute, and you have, that's equal to negative 32 over 3 times the integral of cosine theta minus sine squared theta cosine theta minus 1. So that's going to be, what's the integral of cosine? Sine. What's the integral of sine squared cosine? Well, if you let your u equal sine theta, then your du is equal to negative cosine theta. Is that right? No. Come on. I need to wake up. The du is equal to cosine theta. It's not negative cosine theta, which is present there. So what am I integrating actually? U squared. So that's negative u cubed over 3. So negative of sine cubed theta over 3. Alright, and then the integral of 1 is theta. Let's hope the dentists don't pull as many teeth as I feel like I'm having to do up here. This is like pulling teeth. I have a dentist appointment today. That's why I said that. Alright, so that's going to be the sine of pi over 2 minus the sine of pi over 2 cubed over 3 minus pi over 2. And then that's minus sine 0 minus sine 0, 0 cubed over 3 minus 0.
Isn't that just 0?
Yes, that is 0. 0, 0, 0. Oop. So then that's going to be what? 1 minus 1/3 minus pi over 2 times the negative 32 over 3. So that is negative 32 over 3 times 2/3 minus pi over 2. Now you may want to make sure that that's going to be a positive value, right? It is, because you get a negative inside the parentheses. Could that be simplified a little? Yes, you could clean it up a little bit. You should get about 9.64 if you work that out. I had somebody on my Cal 2 test that did the area between the two curves and gave me a negative answer. Remember, area and volume, we can't get negative answers. If we do, we mess something up.